Thank you very much. Thank you. So let me introduce Mr. Stéphane VALANCE. He has a PhD in numerical method and material science. He has worked in several places from Austin in Texas to Switzerland and is now at SEA, working on behavior of reactor fuels responsible for the LEU-FOREVER Horizon 2020 projects. Stéphane, the floor is yours.
Thank you. So my presentation today is on innovative and safe supply of fuel for reactors. I'm doing this presentation also on behalf of Bruno Baumeister, Winfried Petri, and Jan Oglund, who are coordinators of other projects that I will introduce later on. So first of all, just to set up a little bit of context that this here everybody knows about, research reactors and nuclear power plants are the key element of a working ecosystem for nuclear power usage. And the interest is so decarbonated electricity supply, of course, but also, for instance, for research reactors, production of medical radioisotope and high-level science. Now, if you want working NPP or working research reactor, you, of course, need a fuel element. And this fuel element is provided by a fuel provider who basically will take depleted uranium, enriched uranium, structural element, and manufacture a fuel element. And this fuel element will meet some requirement by the nuclear power plant and research reactor, which are given neutron flux in normal operation, safety in incidental and accidental operation, and also cost effectiveness, of course. Here, the three projects I'm presenting have challenges in 2 points for the fuel provider. One is diversifying the suppliers. So it's typically the case for Russian technology reactors who only have one supplier for their fuel. And the second point is to innovate to reach non-proliferation goals, and this targets particularly research reactors, high-performance research reactors, but I will come back to that. So fuel supplier diversification. So for some design of research reactor and NPPs, you have a historic fuel manufacturer from Soviet and so now Russian origin. It's for NPPs, it means VVER technology NPP. There is quite a number of issues linked to a unique fuel provider, and quite rapidly you can think at what happens if the provider defaults. There is no incentive for continuous improvement of the fuel because you have only one provider, so there is no concurrence on the market. And for the same reason, you do not necessarily meet cost effectiveness. In Europe, and this concerns for NPPs, VVR 4040 from Czech Republic, Finland, Hungary, Slovakia, and Ukraine. For research reactor, this concerns Czech Republic, Hungary, Poland, and Ukraine. If you want to meet fuel supplier diversification, you have a couple of challenges to meet. First one is to analyze the key function. So you have to do reverse engineering on the fuel that already exists. You have to reproduce the normal operation behavior. You have to preserve and improve the key safety feature. And you have to propose a cost-effective solution that you can manufacture also. Key points to reach this goal are collaborative approach, including manufacturer, research experts, reactor operator. Also, you have to improve safety and operational feature of the fuel elements, and to include the preparation of the licensing steps as soon as possible. For research reactor with high enriched fuel. So the question here is not a question of diversifying the suppliers, but to meet the target of the Global Fleet Reduction Initiative, where it's stated that your fuel enrichment should be below 20% to 35U. This conversion has already been done for a medium performance research reactor and is technically feasible and ongoing. Now, the last research reactor that remains to be converted are the high performance one. So the challenge is to use a fuel below the 20% enrichment while conserving the reactor performance and to prove and improve the reactor safety usage. So the three projects I'm presenting today are meeting these goals. So ESSANUF project, European Supply of Safe Nuclear Fuel, and LEU-FOREVER are both dedicated to the diversification of sources of fuel supply for VVER and research reactor. Whereas LEU-FOREVER and HERACLES-CP targets also the development of non-proliferant fuel for high-performance research reactor. You can find on the slides a website for each of these three projects, and I, of course, invite you to visit the website. Okay. Now, how did this challenge? How are this challenge being tackled? First, to be cost-effective, an approach which is called design to cost has been put in place. So this is typically for the medium power research reactor fuel supplier diversification, where you input the generic fuel technical requirement and then work together for in the different fields necessary to design the new fuel. You work in a continuous manner to reach a generic fuel preliminary design that meets the design to cost approach. For ESSANUF project, there were also the same kind of approach was used, where design inputs organized around workshop was done. Particularly, there were workshops on fault analysis, fuel rod design, thermal hydraulic design, and nuclear criticality safety. And there was also an extended use of scientific calculation with code coupling and CFD models. With respect to low-enriched uranium fuel conversion, we have right now at hand mostly one effective solution, which is uranium molybdenum fuel, which enables to reach a high enough density of 235U in the fuel. Basically, this is a curve of uranium density versus uranium enrichment. Actual high-performance reactor in Europe are between, let's say, 80% enrichment and 27. The target is to go below 20. And for this, uranium, molybdenum, or U3SI2 with high density are the preferred solution. In the LEU-FOREVER project and the HERACLES-CP, there is a number of advanced tests which are foreseen. So particularly the Semper Fidelis irradiation, which is an irradiation testing the uranium molybdenum fuel capacity. The Empire irradiation, which is done in the US, so not not funded by the Europe, which targets monolithic fuel comprehension, so uranium molybdenum monolithic fuel. And finally, this will lead to a final irradiation effector-free and future mono 1. In terms of results, so for the ESSANUF project, it resulted in a new VVER 440 fuel design with an optimized zero cladding. The fuel rod has been optimized with 3D neutronic calculation. And the design was done so that inspection and repair were possible on the new design. Concurrently, there was an assessment of manufacturing capabilities, and it was estimated that a time frame of 24 months would be necessary to establish a full production chain, and 24 months were also necessary to license fuel transport containers. For the medium power performance research reactors, there is so several workshops have been organized within the LEU-FOREVER project. Resulting from this workshop and the work from Technicatum, a preliminary design was proposed, and you can find several communication on this preliminary design in the RRFM of this year. Finally, for low-enriched uranium conversion, so the Semper Fidelis irradiation campaign reached its end this spring. So 11 plates total were irradiated. One plate with a 4-cycle showed no failure sign, so this is a very encouraging result. And within LEU-FOREVER, depleted uranium plate for high-loaded U3Si2 were manufactured, and also the proven feasibility of gradient monolithic uranium molybdenum fuel on surrogate material was done. Okay, so this is a compilation of all the communication that have been done within those 3 projects. And to finish with, so the objective here was to secure the supply chain of nuclear fuel, both for NPPs and research reactors, and to reduce the proliferation threat with respect to low-enriched uranium fuels. The main achievement are the design of a replacement element for VVER 440, test of reliable conversion fuel for high-performance research reactor, and the design of a conversion element for medium power research reactor. Thank you.
Thank you very much. Are there questions? Yes, please.
Jan Valenius from KTH Stockholm. You showed the composition of the research reactor fuel, which seemed to contain zirconium nitride. What is the function of the zirconium nitride?
Yes, so what you can see here is a typical dispersed uranium molybdenum fuel. So you have a molybdenum phase dispersed in an aluminium matrix. And one of the problems with this is that you have a tendency to form an interdiffusion layer between the uranium molybdenum particle and the aluminium matrix. And this interdiffusion layer is really bad, so to say, when coming to efficient gas retention and mechanical properties. So different solutions are being tested to prevent the formation of this interdiffusion layer, one being the use of zirconium nitride coating on the uranium molybdenum particles.
Okay, thank you very much.